Okay, so you want to do an example of a conservative field, and here's the theorem that we wrote on the board in the previous clip. So we're going to write down a field. We're going to check to see if it's conservative using this property, which is the easiest to check. It's just a matter of calculating derivatives, partial derivatives. Once we know that, we're going to find its potential function. Once we have the potential function, we're going to be able to calculate line integrals very easily by just plugging in the values at two endpoints. So let's do that. So F is the field. This example is taken from an exam question, so it's stated in an exam-like sort of way, but the idea is, of course, the same. So F is going to be the field A, Y, Z plus X in the I direction, plus 2xz in the j direction, plus bxy plus z in the k direction. So this is the given field, where a and b that you see here are parameters. Okay? And part one was, find the rotor of f. I'm not going to write all the parts of the problem, we'll just do it. So part one was find the rotor. So the rotor of f is I, j, k, the components of the nabla operator, d to dx, d to dy, d to dz, and then the components of f, a, y, z plus x, 2xz, and bxy plus z. Right? Now we're going to calculate this determinant. So in the I direction, we have the derivative with respect to y, so it's bx minus 2x. That's the I component. In the j component, we have by minus ay, and all of that in minus. So let's write ay minus by. Right? by minus ay in minus, so ay minus by. And in the k direction, we have 2z minus az. 2z minus az. This is the curl. Good? Okay. Part two was, find all the possible values of a and b such that the curl is 0. So that's, again, very simple here. For the curl to be 0, all the components have to be 0. It's a vector. So here, for the I component to be 0, you need b to be equal to 2, right? For the k component to be 0, you need a to be equal to 2. And once a and b are equal to 2, that makes the j component 0 as well. So the only possible solution is for a equals b equals 2, the curl is 0. Good? Why what? Here?
No, this next one.
Why is this the... What's the question? Good? Okay. So for a equals b equals 2, the curl is 0. Okay. Part 3, so once we know that the curl is 0, by that theorem, that this is part 4 of the theorem, so for a equals b equals 2, the curl is 0, therefore it's a conservative field. Okay? Good? Since it's conservative, it has a potential function. That's part 3. So part 3 of this example is, let's find the potential function. Find phi of x, y, z, it's going to be a function of 3 variables, such that our given f is the gradient of phi for the values which guarantee that, for a equals b equals 2. Okay? So the question was phrased, for the values that you found in part 2, find the potential function for f. Okay, so let's do that. I'm going to rewrite f on the next board, replacing a and b with 2, and then I'm going to find the potential function. So f is now PQR, where P is 2yz plus x, Q is 2xz, and R is 2xy plus z. I replaced A and B with 2. So this is our field F now. And what I'm looking for, so we want a function phi, a scalar function phi, that satisfies the following. The derivative of phi with respect to x has to be equal to p. The derivative of phi with respect to y has to be equal to q. And the derivative of phi with respect to z has to be equal to r. That's what it means for the gradient of phi to equal to f. Right? Everybody good? Okay. So we did similar examples for 2 dimensions. It's exactly the same idea, the same method. So I'm going to take, for example, I'm going to start with this one because this one just looks, well, the easiest, but you can start with any one you want. Okay? So I know that the derivative of phi with respect to y has to be 2xz. So phi itself has to be the integral dy of 2xz. Do you agree? So from this it follows that phi itself, x, y, z, has to be the integral of its derivative with respect to y, which is q, which is 2xz, integrated dy. This is an indefinite integral. I'm just looking for the antiderivative. Okay? And this is very easy. So this is just 2xyz. The derivative of this with respect to y is 2xz, right? Satisfies this. But plus what? Right. In general, a constant. In this situation, it can be any function that doesn't have y's in it. If it doesn't have y's in it, its derivative with respect to y is going to be 0, and still the derivative of the entire thing is going to be 2xz. So this is plus some function of x and z. Does everybody agree? Okay, so this is phi. At least this is the component of phi that has y's in it. Okay. Now what do I want to satisfy? I wanted the derivative, let's do this one now. The derivative of phi with respect to x has to be equal to this. Okay, so d to dx of our candidate for phi, 2xyz plus f of x and z, has to equal 2yz plus x. So what's the derivative with respect to x of this thing? So it's 2yz plus the derivative of f with respect to x. Good? That has to equal to 2yz plus x. Clear? And therefore, what is the derivative of f with respect to x? Has to be x. So the derivative of f with respect to x has to be x, from which it follows. This is again an indefinite integral. I'm just not going to write that f of xz is the integral of x dx, which is x squared over 2. Right? So f of xz, I just said I'm not going to write it, but let's write it. fxz is the integral of x dx, which is x squared over 2 plus, not a constant. Right, something that cannot have x's in it, but could have z's in it. So plus, let's call it g of z. Good? So now we know we can, this is f of xz, we can plug it back into here. So now we know that phi of xyz is of the form 2xyz plus x squared over 2 plus something that has only z's in it. Okay, so at this point we know that phi of xyz equals 2xyz plus x squared over 2 plus something that has only z's in it, g. Okay? So there's one more step, and there's one more chunk of data that we didn't use. We didn't use yet the fact that the derivative of phi with respect to z is r. That's the one partial derivative that we didn't use yet. So the derivative with respect to z of this thing, 2xyz plus x squared over 2 plus g of z, has to equal to r, and r was 2xy plus z. Okay, so this is the third thing that we know. And from this it follows that the derivative with respect to z, 2xy plus 0 plus g prime of z equals 2xy plus z. And again, g prime of z is now z. Therefore, g of z, g prime of z is just z. And therefore, g of z is z squared over 2. And now it's plus a constant. Okay, one second. So the bottom line is phi of xyz is 2xyz plus x squared over 2 plus g plus z squared over 2 plus a constant. That's the form of a function whose gradient is precisely the given field f, and you can verify it. Just calculate the partials and see that it's precisely what you get for our field f. Okay? So it looks like kind of tedious, but actually it's nothing. What we did now is really easy. It's just a matter of careful bookkeeping and remembering which variable you're integrating with respect to and which variable you're taking the derivative with respect to, but it's very standard, very easy. Okay, good? Question?
Yeah, why can't g be a function of the z and y?
We already know, so the question was in this board, why can't g have y's in it? Well, remember what f was. F was the y-less part of phi. Everything that has y's in phi has to live here, right? So f can only be a function of x and z, because its derivative with respect to y has to be 0, okay? And g is a component of f, so g can't have y's in it. And it can't have x's because everything that has x's in it is already here. Okay, good? Okay, so we're not done. We're not done. What we did now was find phi such that f is the gradient of phi. Okay? And part 4 is calculate the line integral of f dot dr over a curve called C in this problem. And the curve is given, it's a 3-line story. What is this curve? C is, let me write that. We're going to need some more space. So let's erase here. So I'm rewriting this. We want to find the integral, the line integral, the work done by f over some curve C, where C is a part of the circle, x, y, z, all the x, y, z's, satisfying that x squared plus y squared equals 1 and z equals 1. So if you think for a minute, this is a circle, a unit circle sitting up there at z equals 1. Do you see that? That's what this is. And C is part of the circle connecting the 2 points 0, 1, 1, which is a point on this circle, 2, 1, 0, 1, which is another point on this circle. So it connects this point to this point. It's on this circle, so all that remains is to say in which direction I'm going. Because I can go like this from one point to another on the circle, or I can go like this from one point to another on the circle, right? So connecting these 2 points in the direction which is counterclockwise, when viewed from above. Wait. So note that saying what C is like 4 lines, and this is an easy example. Okay, some examples tell you a huge story of what C is. The point is, we don't care what C is. Why? Because F is conservative. And once we know what path we want, that it goes from here to here, I don't care if it goes counterclockwise or clockwise, or along this circle or not along this circle, or goes in some squiggly, crazy way. Doesn't matter. This integral equals phi at the end point minus phi at the starting point. Clear? That's precisely this statement of this theorem. If we know that if we know that f has a potential function phi, then the integral from a to b doesn't depend on the path itself, only depends on the value of the potential at the end minus the value of the potential at the beginning. The difference in the potentials. Okay? So the answer here is, you can do it. You can calculate it using a line integral. In this case, it is probably even calculatable, but it's a lot easier once we found phi. So the integral of f on this curve C dot dr is phi at the end point 1, 0, 1 minus phi at the starting point. And phi we know, we just calculated it. So let's look at what phi was again. This was phi, remember? So we need to plug in 1, 0, 1. So when we plug in 1, 0, 1, this dies. This becomes 1/2. This becomes 1/2. You can choose C whatever you want, or you can just leave it as a C, because it cancels when you do phi at one point minus phi at the other point. So this is going to be 1, 1/2 plus 1/2. And phi at 0, 1, 1, this is again 0. This is 0. And this is 1/2. So it's 1 minus 1/2. 1 minus 1/2, which is 1/2. Very easy once you know the potential function. Good? Questions? No questions? Okay, so really it's the same idea as in 2 dimensions, and really it's not complicated, and really it pays. So this example was really spelled out for you in the steps you need to take in order to kind of reach this conclusion. In a general case, the problem could just be this. Here's a field f. Calculate the line integral, pa-pa-pum. And in many cases, it pays off on your own to think of, hey, wait, is this f conservative? Easy to check. Just check the determinant of the curl. Oh, the curl is 0. It is conservative. Let's find the potential and do this rather than get involved with actually calculating line integrals, parametrizing curves. And in this case, it's easy to parameterize this curve. So doing it the straightforward way is probably not that difficult either. But in general, this could be much easier than calculating directly line integrals. Okay, question? Yeah?
Do we have to state at the beginning that f is in C1?
If you're going to use this theorem, then you have to say that f is in C1. And we said it. We said that this field is obviously, I mean, this is just a polynomial in the three variables. It's obviously in C1, and the entire R3, there's no obstacle to using the theorem on any region. Okay? Maybe we forgot to say that, but you should.
If it's not in C1, like if only like have divided by x plus y.
Right. When there are singular points, you cannot use this theorem as is. We discussed an example at length for the two-dimensional case, and there are examples in the three-dimensional case, and then you have to do more careful analysis. So if you have a curve that is in a region where it doesn't go around, and note that around is more loose here, because you can go around a point, but you're in three dimensions. You're around the point, but you can still be in a... So here's a side remark. Here's the origin. Suppose a field has a singularity at the origin, and you have a curve that looks like, let's take a different color. You have a curve that looks like this, for example. Does this curve go around the origin? Okay, all you need to do in order to use this theorem is to be able to use Stokes. You need to be able to put a surface above this curve. So if you take your domain V to be, let's say, something like this, okay, this is three-dimensional. I don't know if you can see, but it's kind of like something like this. This contains the curve. It looks like the curve is going out of it because there's a bad drawing. If you take half of a helmet sitting right above here, and the singularity point is inside, but the curve is in the helmet, then you're good. Do you understand what I'm saying? Okay, so there are subtleties, and you have to be careful, and one can take this to a broader discussion. And then there are more delicate versions of the theorem that say, suppose that it is singular at some point, singular meaning that it doesn't satisfy the C1 condition, or that the V is not simply connected, and how to get around that. But that discussion is long, and we're not going to do the details now. Okay. So that's the end of this clip.